Then, hello everyone to today's seminar on interval methods and control engineering. And it's my great pleasure today to introduce Shuang Zhang, who did her both bachelor and master studies in control and industrial engineering at the Harbin Institute of Technology in China. And after that, she moved to Spain, where she's currently working as a PhD student in automatic control and robotics in the research group of advanced control systems, which is headed by Vincent Buch. And yes, this research institute is situated at the Universitat Politècnica de Catalunya in Barcelona in Spain. And I'll now hand over the microphone to you, Shuang, and you will present something on robust fault detection using set-based approaches for LPV systems. The floor is yours.
Okay. So now I start?
Yes, please go ahead.
Okay. Hello, guys. I'm very glad to present my recent work about robust fault detection using set-based approaches for LPV systems with application to autonomous vehicles. This work is done under the supervision of Professor Vicens and Sala. I will talk about these 5 parts. The first part is introduction and the problem formulation. Firstly, this diagram shows the main structure of this talk. We focus on the problem of robust fault detection for autonomous vehicles in LPV form using the set-based approaches. As we know, autonomous vehicles could bring many benefits, such as reducing traffic crash, saving energy consumption, and improving traffic efficiency. Consequently, for this safety critical system, it's very important to diagnose faults that may happen in sensors or actuators. So here we propose 2 approaches for robust fault detection, direct test and inverse test using LMI-based set membership for state estimation and parameter estimation respectively. Firstly, a lateral dynamic vehicle model is given in terms of the 2 degrees of freedoms bicycle model, where the set slip angle and the beta and the yaw rate phi are the states, and the front steering angle is as input. The lateral velocity Vx is regarded as the scheduling parameter. Then the LPV model can be obtained in this form after the discretization. Furthermore, the LPV model can be further transformed into the polytopic framework, since it offers a convenient way to represent and analyze LPV and uncertain system. AI and BI are the correspondent vertices dependent on the parameter theta. Mu is the membership function. In order to improve the safety and the reliability of the autonomous vehicles, fault detection is quite essential. It has to do the consistency check based on generating the residuals between the estimated behaviors from estimator and observed behaviors from sensors. Actually, the residue should be only affected by faults. However, the built model is always affected by some uncertainties, such as modeling uncertainty, unknown noise, and the disturbance. So the fault detection process must be robust against these uncertainties. Hereby, set-based approaches provide an unknown but bounded description for modeling the uncertainties. So in this work, we will research the set membership based on robust fault detection using zonotopic sets. Besides, we will use a passive approach to finalize the robust fault detection, which is based on residual generation. The residual can be generated in output space or parameter space, which is corresponding to direct test and inverse test respectively. In the direct test, the residuals are generated by the difference of the measured output and the estimated output. Then the fault detection test checks if the measurement output is inside the interval of the possible values. Here we consider the interval is because we have to include the effect of uncertainties. Then the direct test can be implemented by state estimation. I will explain how to implement in the next slide. And in the inverse test, the residual is a nominal parameter minus the estimated parameter. So it's equally based on checking if there exists a parameter inside the set of nominal parameters that enables the model to be consistent with the measurements. Then it can be done by checking if there's intersection between the estimated parameter set between the measurement strip. If the intersection is empty, then we can see there exists a fault, and how this inverse test can be implemented by parameter estimation. I will illustrate how to implement in the third part. In the second part, I'm going to talk about how to use state estimation to implement the direct test. Let's first get familiar with set membership for state estimation for LTI system. The set membership estimation process consists in 3 steps: prediction step, measurement step, and the correction step. In the prediction step, it has to compute the uncertain state set, which represents in yellow. And in the measurement step, it will compute the measurement consistent state set from the measurement output. And finally, in correction step, it will compute an outer approximation of the intersection between the uncertain state set and the measurement consistent state set. Here we describe the size with zonotopes. C represents the center, R is the shape matrix represents the uncertainty. So the uncertain state site and the intersection site can be propagated by center and the uncertain separately to avoid the wrapping effect. And the intersection site can be computed in this way. In order to have an optimal approximation of the intersection, the optimal lambda is obtained by minimizing the Frobenius norm of the shape matrix. But this method is especially for LTI system because our autonomous vehicles is in LPV form. So we propose this LMI-based set membership for state estimation to adapt to the polytopic LPV form. So you can see in the prediction step and the correction step is designed for each text system. And then combined together by the membership function. It's worth notice that the lambda is also designed for each text system. And then to get the optimal approximation of each intersections. In order to obtain the optimal lambda, the previous way by minimizing the Frobenius norm of the shape matrix is not a good choice because it can't provide a polytopic lambda. So we prepare such LMI for each text system and solve the optimization problem online. Then we can get a series of lambda. And then the optimal lambda can be combined together online. After getting the estimated state, we can start fault detection by checking if the intersection is empty between the uncertain state site and the consistent site. When the system is healthy, the intersection is always exist as shown in this figure. If a fault appears, the consistent state site will move away from the uncertain state site. So when the intersection is empty, we can say there exists a fault. In this third part, I will explain the parameter estimation for inverse test and the relation with state estimation. As we know, the state estimation could apply for parameter estimation by this formulation. So the LPV system can be expressed as another LPV system in this regressive form when we only consider the second output. Here, C is the regressive vector. It contains the fractions of inputs and outputs. Theta is a parameter vector. It contains the second row of parameters, A21, A22, and B2. These are the parameters we are going to estimate. To consider the uncertainty, we assume the parameter is inside this zonotopic site. Here P is the center and H is the shape matrix. Then the set membership for state estimation can be done following the same process as state estimation. That is the prediction step and then correction step. After applying to this reformulation, due to A is the identity, B is 0, and E is 0. So this prediction step can be omitted, and then we can directly do the intersections correction step. And also the optimal lambda is still obtained by minimizing the Frobenius norm of this shape matrix. For the RMI-based set membership approach, for parameter estimation, we compute the optimal lambda by solving RMI. This RMI is also from the state estimation after applying this reformulation. We find if this RMI is totally the same without change from this RMI, the result is a bit conservative for parameter estimation. So we design a varying shape matrix and then solve this optimization online. Then we can get the optimal lambda. In return, this lambda can provide a better estimation accuracy. At last, the fault can be detected by checking the intersection between the estimated parameter set and this measurement stripe. When the system is healthy, the intersection exists, but when fault occurs, the measurement stripe will move away from the parameter site. So here, so in this way, we can detect the fault. So far, all the methods are ready. Here we apply the methods for simulation test. Firstly, we do state estimation for these autonomous vehicles using the proposed RMI-based set membership and the classical set membership for comparison. The estimated states are the set slip angle beta and the yaw rate phi. In this plot, the red line represents the proposed LMI-based method, and the green line represents the classical set membership approach. It can be seen that the performance of these two methods for theta estimation are almost the same. And for parameter estimation, we estimated these three parameters using the proposed LMI-based method and the classical set membership approach. And also the red line represents the proposed method, and the green line represents the classical method. We can see the performance of these two ways are quite close, but the proposed method could converge faster. As a conclusion, combining the results of the state estimation and the parameter estimation, we can get the proposed LMI-based set membership method is a good alternative to the classical method. In order to conduct the consistency test, we inject two types of faults to these autonomous vehicles. The additive faults occur outside of the system that may affect actuator or sensor. We introduce the actuator fault, input sensor fault, and output sensor fault. The multiplicative force will affect the system parameter. So we introduce the force on CF and SA, then these three parameters are all affected. First, we do the consistency test for additive force. As we can see, first we see the output for detection case. By the direct test, the measurement output is outside of the interval of estimated output at around the time instant 1000. So it means the fault occurs after this time. And then in the inverse test, the parameter set is not intersected with the measurement stripe. It also indicates the fault. But when we do the direct test and inverse test for input fault detection, we can see the direct test can show the fault after time instant at 300. But the inverse test case, there exists intersections between the parameter set and the measurement stripe. So the inverse test can't detect this fault. Besides the actuator fault detection case, both direct test and inverse test can detect this fault well. So as a conclusion, the direct test is effective for all the additive faults, while inverse test is partially valid for additive faults. For the multiplicative fault case, we can see for the inverse test for these two cases, there is no intersection between the measurement stripe and the parameter set. So the inverse test perform well for the multiplicative fault. The direct test could detect these faults, but it's not quite obvious, and the detected time instant is not consistent with the actual fault occurred instant. In this case, this time the direct test time is a bit later than the actual time when fault occurs. So we can get the conclusion that direct test can't provide good performance for multiplicative fault, while inverse test works very well for multiplicative faults. So here, as a conclusion, in this work, we propose an LMI-based state parameter estimation methods for LPV systems. And this LMI-based set membership is a good alternative to the classical set membership. Especially for parameter estimation, it has low efficiency, but it has high response and quick convergence. Besides, the direct test has better performance on additive faults, and the inverse test has better performance on multiplicative faults. So as for the future research, we are going to find the minimum detectable fault to describe the detectability of this method. And then during the research, we found that if we only employ one polytopic LPV system to describe the autonomous vehicles, the estimation is quite conservative. So we are going to research on a switched LPV system to adapt to the whole range of parameters. That's all. Thank you for your attention.
So many thanks, Shuang, for your presentation. And I'm pretty sure that there will be someone who wants to ask some questions. Who wants to start? So I see the very first question from Carlos.
Hi, do you hear me?
Yes.
Yeah.
Okay. Thank you for very nice talk. I really like it. It wasn't quite illustrative, I think. And I just wondering, is you show, or you said that basically in the conclusions, we have that the inverse problem is better than the set membership for multiplicative fault.
Yes.
So have you think why is like that? And have you seen in some alternatives to improve this result and you can become better or something like that? It's more about future work. What do you want to do, or it's just like, okay, we're going to stop there because there are nothing much to do. Yeah, it's basically around that.
For these results, inverse test is better for multiplicative fault. Because the multiplicative fault is affecting the parameter system parameter. So and also this inverse test is conducted in the parameter space. So I think that's why it can provide a better performance than the direct test. But for the further reason, we haven't investigated much because when we do the inverse test parameter estimation for LPV system, we encounter some problem. It's like here. We can only conduct this optimal lambda online. So it's not, we can't provide a better results. So when we consider the polytopic system, the results is quite conservative. So it's still under research.
Okay, thank you. No, that's all from my side. Thanks a lot. Yes.
Okay, then I see that Tarek has unmuted himself.
Yeah, I have a question. Awesome. Thank you very much for this very nice presentation. Could you please put slide 7? It was not clear for me how have you transformed the model to consider parameter estimation. It was not clear for me. Could you please explain the steps to transform the model?
The transform to the model.
Yeah, please.
Here, so this model is previous in the LPV form, the state and the input, and here we want to transform. We only consider the second output, this phi. So its phi is composed by the this line times this line and plus the input vector. So here we regard this theta as the state. Then theta k plus 1 equal to theta k. So A is equal to the identity, and then B is 0. And then here theta as a state, then the regressor form, the C vector includes this states and the input. So here is how to transform to this regressor form. Did you?
Yeah. Okay. Yeah. Okay. Okay, thank you. So, do you need some persistency of excitation assumption or something like that to know? For the identification for the parameter estimation, do you need that the inputs of the system may be exciting or something like that? The identification, I don't know if here for this technique, if the identification, the parameter estimation depends on the input or no of the system.
So you mean here the input?
Yeah.
The input is known.
So you don't need any additional assumption such as persistency of excitation. You need only the detectability of the system. Is it true, or do you need some other assumptions and conditions? How to prove that the estimation, the parameter estimation, will converge?
Will converge. So you mean the stability analysis?
Yeah, maybe for fault detection, we need that the estimated set, for example, the zonotop, should be not very large. So how to ensure that with this technique, the zonotop, the set will converge to a small set?
So here
to reduce the rate of non-detected faults, for example.
So here we compute
yes.
it's implemented by this lambda. We compute it as the optimal lambda. It can satisfy the stability property and also a tighter approximation of this intersection.
Okay. So thank you very much for this very nice presentation.
Thank you.
Okay, Xu, please go ahead.
Yeah, I have one question for the application part. And I see in your resource, you consider the single fault case. That's right?
Yes.
Okay.
We only consider the single fault.
So is that possible for the multiple fault case or not? Maybe it will be interesting, I think.
multiple fault case, if the multiple faults don't occur at the same time, then it's possible. If the same time all the faults occurred, maybe the effects will eliminated. So if it's not the same time happens, this work could affect.
And I have for the fault you considered, and for the dynamic fault, for the parameter fault, you consider it as a multiplicative fault. And actually, for me, you can also consider it as an addictive fault. So I don't know if you tried this or not. I think maybe it will have the similar results in the actuator fault or sensor fault.
You mean? Do you mean that for the actuator fault? So, sorry, I didn't catch.
So yeah, I mean that for both for actuator fault, sensor fault, or parameter fault, you can all consider them as an addictive fault or the multiplicative fault. So I don't know why you only consider the parameter fault as a multiplicative fault. Yeah.
Because here the actuator fault, the sensor fault happens outside of this system.
Yes.
So it's added plus. So it's added after the system. Then we assume that it's the additive fault. I think it's, if you consider the system with actuator or sensor, if you assume the system contains the actuator, then I mean, if you consider a larger system, then it might be the multiplicative fault. But in my case, I only consider the physical system, not include others. So it's assumed as the additive fault.
Okay, got it. Yeah. Thank you very much. And that's all my questions. Thank you.
Thank you.
Okay, do we have any further questions in the audience?
Hello, can you hear me?
Yes.
Yes. I want to know, does this techniques can achieve fault estimation? Because you can detect every fault, so can we lock it to location?
Sorry, can you repeat?
Can we achieve fault estimation?
Fault isolation. Fault isolation. Here in this work, I haven't considered the fault isolation. Now I only detected the fault. For the isolation, I think it's possible. It's possible if we, because the fault, the size can be described by zonotope, and then if the if, for example, if the actuator fault zonotope with the output sensor fault the zonotope separated, then it can separate these two faults.
Okay. You mean both the accurate fault and the sensor faults can, which we influence the top, so we only can achieve fault detection, but not achieve false isolation in the at present.
So currently we only detect the fault. If we isolate the fault, we need to characterize the residue.
Okay.
Maybe let me add directly a question to this. Isn't this related directly to the thing that Tarek just asked before? Because if you can prove observability of one of the components that you want to estimate, for example, if you're proving that you can directly estimate the parameter CF, for example, if you have proven observability of the corresponding quantity, I think then the fault isolation is directly possible.
Yeah, okay.
Because then you know directly in which quantity the errors have occurred.
Okay, thank you for your answer.
Yes, at least my feeling there is it should be related to the observability of the corresponding quantity. Okay, then I see a further question in the audience. Xingyao?
Yes. Thank you also for your interesting talk. I have a very general question. So it's about like here on this slide, you have different kind of faults, and do you have like some general idea about the sensitivity of the detection? And is there any difference that when you detect different kind of faults? And maybe, like do you have like a minimum magnitude of fault that you can detect? Yeah, this is my question.
Here the minimum detectable fault is the next step as I conclusion. Yes, we too want to see the sensitivity for the different faults. So in the next step, we will see the minimum detectable fault to basically by the residue, the zonotopic residue between the healthy zonotopic faulty residue with the healthy zonotopic residue. Then if these two residue sites are separated or touch or just a touch, then we can say it's a minimum detectable fault.
So you mean that's the sensitivity will also dependent on the, let's say, the size of the zonotop, right?
Yes.
Okay. Okay. Yeah. Yes.
I mean, in the previous work, someone do the minimum detectable fault by intervals, but we do this work by describe the size by zonotopes. So it could describe the site by tighter, but tightly describe the site. So then the minimum detectable fault could be improved and more accuracy results.
Okay. And do you maybe have a like rough idea about the different kind of faults? Are they same? I mean, the sensitivity of the detection. Are they same, or they should be? There should be any difference?
You mean in different faults the sensitivity should be different?
Yeah, exactly.
But now I'm sorry, I don't have such idea.
Okay.
As which position the fault will affect the sensitivity.
Okay, yeah.
I will explain.
Mm-hmm. And may I ask one more question about the applications? So here, maybe the next 2 slides. Yes.
So this additive fault?
Yes, can you maybe explain more? Because I'm not familiar with this application. So maybe can you explain a little bit on the how the fault is defined here and what they are represented for?
Okay. So here let's see the output fault detection. Here this red line represents the estimated output, and this black line represents the measurement from the sensors. So here we injected the fault, the output fault. So here we can see the measurement output is outside the estimated output. Then we can get that fault occurs. If you can see this figure, this is a measurement, and this is estimated. So when fault occurs, there's no intersection. So that's how the fault detect. And then the inverse test is done in the parameter space. So here is a measurement stripe still from the sensors. And here is the estimated parameter set is in zonotopic set. So when the zonotopic set parameter set is not intersected with the measurement stripe, we can see there's a fault. Not
Yeah.
sure if you are more clear.
Yeah. Thank you very much.
You're welcome.
Okay, concerning this parameter estimation, I would also like to ask a question. Maybe you could open again the slide number 7.
Parameter estimation.
Yes, I think it was the slide 7 that you already discussed with Tarek before, where you have modified your system model.
This one?
Yes, this one, exactly this one. As far as I get it correctly, what you're estimating directly is the entries in your system matrix, in the original system matrix, and also the entry in the input vector.
Good question.
Yes, and the question there, let me continue the question first.
Okay.
The physical reason for why I'm asking this is those parameters, they depend not only on inertia properties, this is a capital I, but they also depend on, for example, parameters that are related to road characteristics, for also stiffness parameters, which may depend on, let's say, for example, friction parameters that are typically varying in practice due to different road conditions. Now, when you're estimating constant parameters in your approach, and I think what is there in this orange box is just you're describing the parameters to be estimated by a discrete time integrated disturbance model. You say new parameter is equal to the old parameter. That's the matrix capital A is equal to identity matrix. You don't have any external input. That means B is equal to 0. And your second line of the system model, this with a shaded background, is being interpreted as an output. Now, what you cannot estimate is parameters that are varying over time or varying also over the run of your vehicle from one position to the other, because you always say you're searching for something within the sonotop that will be a subset of the previous estimate.
Yes.
What I was wondering is, would it make sense to introduce something like some kind of forgetting factor in order to allow also for temporal variations of the parameter? That means you would have to add some kind of prediction step in which your sonotopes start to blow up, and the corresponding correction step then afterwards would do some tightening. I think, at least from a practical perspective, what this system model is used for, this would make sense.
Oh, okay, many questions. As I remember, the first question.
The first one was really treating the parameters in the system matrix as the quantities to be estimated.
Estimate. Okay. Actually, we can estimate. For example, the IZ or LR or other parameters. But here we consider this A21 as a parameter. So it's more simple way to estimate the parameter. If, for example, if we estimate a specific parameter like LR, then we have maybe we have to know we have to assume other parameters are known.
Yes, definitely, but
the...
LR is not a good parameter in this case, because LR is
LR is low. Yeah.
This is the distance between the center of gravity and the rear axis.
Yes, yes.
CR would be a much better parameter because this is typically varying over, yes, due to road conditions.
You mean, but here CR is not varying in my case.
Yes,
only
it's not varying
K.
in your. It's not varying in your assumption, but in practice, it is definitely not constant.
Yes.
And therefore, I really would like to suggest to take into account some kind of forgetting factor in your model, that you allow for temporal variations. That means what you would have is this augmented system model for parameter identification is practically the same as before. You have A is equal identity matrix, but you would add some additive term in each prediction step that leads to some widening of the sonotope.
You mean at each iteration the uncertainty is injected?
Yes. In a prediction, and in the correction
yes,
you have a tightening.
How to get a converging zonotope? You mean?
I'm thinking of something. If you would perform something like a least squares parameter identification, including forgetting factors, you could reformulate this in a stochastic setting as some kind of Kalman filter. The corresponding Kalman filter would have, as in your case, the identity matrix as a system matrix, but you would inflate the corresponding estimated covariance matrix for the estimated parameters in each prediction step. You would have something 1 over the forgetting factor multiplied with the covariance matrix. And in your case, there's an inflation of the sonotope from one discretization step to the next before updating the parameter estimate.
Yes. Actually, this idea is from the stochastic Kalman filter. They do the Kalman filter for state estimation, and then they use this reformulation. They can do it for the parameter estimation. So in that case, in the deterministic case, I also use this reformulation.
Yes, it's a Kalman filter formulation or a linear least squares estimation without forgetting factor that you're using. And I'll send you afterwards a link where you can see how to modify this model to include a forgetting
Okay, sorry,
factor.
I don't know how to do also forgetting factor.
Yes, forgetting factor.
Sorry,
It's just,
I don't know.
yes, previous estimates are being treated much less than the current measurements.
Okay.
Yes, I'll send you a link afterwards.
Okay, thank you.
Yes, and then I only have one final question to the slide. I think it's the next one, to the slide 8.
Here.
Yes, because you have written there that you're solving this LMIs online.
Yes, yes.
Did you check if your estimation algorithm is real-time capable? Or did you just test it in simulations where the discretization step size and also the time requirements for solving these LMIs didn't matter?
Now we only check it only in the simulation test.
Okay.
But actually, this is not a great idea so far. So we try to make it offline, but the offline results is not great. It's not good than this one. So, so it's a temporary result.
Yes, because it's definitely a heavy task if you want to determine all the decision variables, those matrices W, for example, and Y, and also this parameter lambda in real time in each time step. Maybe exists some idea to do some kind of hot restart that you can use the results from the previous discretization step in order to resolve the LMIs.
Yeah.
Okay, but if this is still ongoing work, maybe that's just an inspiration.
Yes. I still have a lot to do.
Great, many thanks. Do we have any further question? Xu, did you raise the hand again?
Yes, I'm sorry.
Okay.
I realized that I have one more question. So could you please turn to the simulation resource, the page number 13, please? One more before the 13.
Okay.
Yes, so here, for example, for the figure in the right up one, the black line represents the measurements. That's right.
The black line.
Yes, is the measurement that means it is the output of the sensor.
Yes.
And here, in your case, the output fault detection, the fault occurs in the in the sensor, right?
Yes.
But if the fault occurs in the sensor, the output of the sensor should change. Actually, it's the output of the system, it will not change. But if the sensor is faulted, your measurements, that means your output of the sensor should be changed. No?
Yes, I understand your point.
Yeah, why?
Why this plot didn't change?
Yes.
Output fault. Let me think.
Maybe here your black line.
Maybe yes. This from the first output.
The first output.
This you mean the second output.
Which one is the first output? You mean the output of the system or the output of the sensor?
Yes, output of the system.
Yeah. So, yeah, I don't know. Maybe because in my mind, I think if the fault occurs in the sensor, so the output of the sensor should be changed. So I don't think it's a good choice to put the output of the system for the fault detection, you know, because what we can get is the output of the sensor, not the output of the system. if you consider the sensor out. So
you
maybe,
mean output sensor is the most important part?
Yes,
that
that's
we get
why.
the data.
Yes, that's how we
Yes.
can get the. That's what we can get from the system. It's the output of the sensor, not the output of the system. If we consider the sensor is the out part of the system, so.
But here you see the observer.
Yes.
It's the observer is before the fault occurs.
But actually, I think the observer should use the measurement of the system. So that means the observer should use the output of the sensor, not the output of the system. Yeah.
Okay, I will check it.
Yeah.
Okay.
Okay. So.
Thank you.
Okay, you are welcome. And so the second figure has the same problem. Maybe you use the output of the system. So yeah, maybe you can check it later. Yeah.
Okay, thank you.
Okay, that's all. Thank you.
Thank you.
Okay, then let me see. There's no one else who has raised their hand in the audience. Do we have any further questions? If not, I think it's time to thank our speaker again. Many thanks for your interesting presentation. Also, many thanks for the inspiring discussion at the end. And to all of you, I wish you a nice Friday evening, Friday afternoon, and enjoy your weekend. And we'll see each other again soon on Friday in 2 weeks. And our next speaker was just the one who has asked the previous questions. Xu will be our next speaker Friday in 2 weeks. See you soon and have a nice weekend.
Thank you.
Thank you very much. Thank you. Bye-bye.
Thank you.